Welcome back everyone. In this lecture I will complete the proof of the dimension theorem. So, to prove the dimension theorem we need one auxiliary result. So, let me just state that. So, maybe we can state it as part of the dimension theorem itself. So, here is the theorem. So, we take rho be an irreducible representation of G of let us say degree D. So, let rho be irreducible representation of G of degree D. That means, the dimension of the representation is D, and then let us fix an element G in G and assume that the size of the conjugacy class of G, so that to be H. So, this is the size of the conjugacy class that contains G. So, then what we have, so we can actually look at this number. So, H times chi of G divided by D. So, this is indeed an algebraic integer. So, where chi is nothing but the character of rho. Okay. As a consequence, once we know this for all irreducible representation, then we will be able to prove that D divides the cardinality of G. Okay. So, let us see the proof of 2 assuming 1. Okay. Here is the proof of 2 assuming 1. Okay. So, what we want to prove? We want to prove that D indeed divides the cardinality of G. So, in order to actually prove that the D divides the cardinality of G, first we need to actually get that rational number. So, that can be obtained as follows. So, what we will do? We just take the inner product chi chi. So, we know that using orthogonality relation, this is supposed to be 1, but which is by definition is nothing but 1 divided by the cardinality of G and times the sum G in G chi G, sorry, maybe let me call it x chi x chi x bar. So, this is indeed the value of the inner product. So, now if we look at it, so this is going to be giving us the cardinality of G. So, we just multiply by cardinality of G and then divide by the dimension of the representation D. So, then this is going to be exactly equal to summation x in G chi of x divided by D chi of x bar. So, now note that if we take this C1 etc. Cs to be the full set of conjugacy classes of G, so then we see, okay, so let us write C1 etc. Cs. So, this is the conjugacy classes of G, and then let us look at the value of chi on Ci. Okay. So, we actually fix this rho already. So, this is not, this is something we are not changing, this rho is fixed, let us keep that. So, we know it, okay, for all irreducible representation rho, we have that this fraction h chi g divided by d, this is an algebraic integer. So, we are going to use that, and we have made this observation for any irreducible character chi. So, this is irreducible character. So, then we have that the cardinality of g divided by d is nothing but the summation of these numbers. So, now what we can do, we can actually just look at all possible values here that is going to appear. Okay. So, you can actually divide G into the union of these conjugacy classes. So, now if we actually write G as union of these conjugacy classes, then this sum is going to run over I range from 1 to s summation chi of this C I divided by d and then chi of C I bar, because chi is being class function. So, it is going to take same values for all elements of this given conjugacy class C I. So, and this is actually going to be since we are running it over all x in G. So, maybe like we can actually use this is for all x in C I. So, this equality just comes from the fact that you write G as disjoint union of C 1 etcetera C s, chi is being class functions. So, we just combine the values. So, now this actually implies the cardinality of G divided by cardinality of G divided by this D is exactly equal to summation I range from 1 to s again. So, what is going to be these values? So, all these are constants. So, where x is running over C I. So, now we can actually take this h I to be the cardinality of C I, h I to be cardinality of C I. So, maybe let us use cardinality of C I. So, then we will get exactly here the cardinality of C I times the value of chi of C I divided by d. So, that is what we are getting it here times chi of C I bar. So, now look at this term. So, this is the exact term that appears in the statement 1. So, this h chi of G divided by d is nothing but the size of the conjugacy class that contains G. So, let me write it as C G times this chi of G, the value of that conjugacy class when taken by this the character chi divided by d. So, this is indeed nothing but an algebraic integer. So, that is what the statement 1 says. So, that means, so this is indeed an algebraic integer. So, this is exactly the value that we have it there. So, this is basically h I, where h I is the cardinality of C I times chi of G I divided by d. So, this is an algebraic integer, but now look at this value. So, this is nothing but character value and conjugate of the character value. So, this is conjugate of a character value, but already we observed that character values chi of G, they are all actually algebraic integers. So, and conjugate of algebraic integer is algebraic integer. So, this is also an algebraic integer. So, now since algebraic integers form a ring, so that implies that this entire sum, the product is an algebraic integer, this product is an algebraic integer, and this sum is also an algebraic integer. So, that proves that the cardinality of G divided by this D is nothing but an algebraic integer. And since this lies inside Q intersection A, which is G, so that would imply that the cardinality of G divided by D is an integer. So, that proves indeed D divides the cardinality of G. So, modulo we need to verify the fact that, so given element G in G, H times this chi of G. So, given G in G, H times chi of G divided by the degree of the representation, this is indeed an algebraic integer. So, where H is nothing but the cardinality of the conjugacy class that contains G. So, the D is nothing but the degree of the representation which is fixed. Okay. So, this is something that we want to prove. So, here is the proof. So, the proof actually is ingenious. So, it uses some operators that you can actually define using the representation, and they are in particularly G invariant maps operators. So, in particularly we can use those operators to get some relations among them, which involves some equation that we have seen before, like y equal to summation aij yj. So, these kind of equation that we want to prove it for the operators. So, we replace yi by operators, and when we evaluate or take some trace and so on. So, we will be able to get back what we wanted. So, the Schur's lemma is actually indeed very crucially used. So, let me actually define the operators very explicitly, then it will become very clear. So, as before, so we are going to fix this row irreducible representation of G, and D is nothing but the degree of the representation, and chi is nothing but the character of this row. So, now we are also going to fix this set of conjugacy classes C1 etc. Cs. So, this is the set of conjugacy classes of G. So, now we are also going to set Hi to be the cardinality of Ci, and chi I or xi I to be the value that you get it when you apply chi on Ci. So, the value of this conjugacy class Ci when you apply chi on that is we are denoting it by psi. So, these notations I will be using. So, now what we are going to do, we are going to actually construct this following operator. We take this Ti. So, for each I from 1 to S, so you define this Ti, which are nothing but the average sum of all this rho x, where x is coming from Ci. Now, the thing is this Ci is indeed invariant under the conjugacy action of G. So, because of that we will be able to see that these Ti's they are nothing but G invariant maps. So, the claim is they are indeed G invariant maps, in particularly using Schur's lemma there must be some multiple of identity. The multiple is also very explicitly given using the trace. So, we claim that Ti is exactly equal to Hi divided by D chi I times identity. So, this is the claim that we are going to make. So, how do we prove this claim? We prove it in two different steps. First step is, so first we prove that Ti is indeed G invariant map. So, since it is a G invariant map from the representation to itself, so we can see that so let us call the V is the representation. So, then this must be as a step 2, Ti must be lambda times identity on this representation V. So, in particularly we can actually compute this lambda using the trace technique. So, the trace of this Ti is going to be the dimension of V times lambda, but dimension of V is nothing but this number d, the degree of the representation. Okay. So, let us assume step 1 and then computes the value d, the value lambda. So, what is rho x? So, rho x is nothing but rho of x. Okay. Rho is the representation from G to GL of V, which is you can identify with GL of dC, where d is the dimension of the V. So, now what is Ti? Ti is nothing but summation rho x x in Ci. So, now what will be the trace? The trace of Ti, in one hand you get lambda times d, on the other hand this is going to be summation the trace of rho x x in Ci. But what is the rho of trace of rho x? So, this is exactly equal to the character value applied on this x. So, that means, so this is exactly summation chi of x, x is in Ci, but chi is class function. So, that means it takes same value for all x in Ci. So, that gives us, this is exactly the cardinality of Ci times the value of chi on Ci. So, this Xi is nothing but chi of Ci. So, from this you can see that let me write it here. So, lambda d is exactly equal to hi times Xi. So, that means lambda equal to hi Xi divided by d. So, this is what we wanted. So, that is, so I am using, this is Xi. So, this is exactly chi of Ci. Okay. So, let us actually prove step 1. So, step 2 is just direct computation using the traces. So, first we need to verify that Ti is a G invariant map. So, let us verify that actually simply follows from the conjugation action on G, which leaves Ci invariant. So, we need to verify that rho G Ti rho G inverse. So, maybe I will use, because I have fixed G. So, let us use something else. Let us use G dash rho G dash Ti rho G dash for G dash in G. So, this is going to be equal to, we want to prove that this is exactly Ti, but this is by definition is going to be rho G dash rho x rho G dash inverse x in Ci. So, then this is exactly equal to summation rho of G dash x G dash inverse x in Ci. But it is easy to prove that from Ci to Ci we have this map x goes to G dash x G dash inverse. So, this is indeed a bijective map. So, the inverse map is given by again by taking the conjugate with respect to G dash inverse. So, that is something very easy to see. So, that means this is exactly equal to Ti. So, this is just simply follows from the fact that Ci is invariant under the conjugate action of capital G. So, that proves that Ti is indeed a G invariant map. So, by Schur's lemma we know that Ti must be lambda times identity. So, that actually completes the proof of 1 and 2. So, now what we will see that Ti indeed behave exactly like algebraic integers. So, that actually that we have seen in the second lemma. So, we will indeed prove that. So, there will be some integers a I j k such that whenever you multiply t I and t j, you get exactly equal to summation a I j k t k. So, there exists some a I j k integers. So, where these a I j k, they are all integers such that, so this actually happens, t I t j is linear combination of t k. So, indeed this is kind of routine calculation. So, we just simply multiply t I and t j and see what happens. So, we just take t I t j, which is exactly equal to summation rho x x in c I times rho y y in c j. So, now if you just multiply and expand, you get exactly summation rho of x y x in c I and y in c j. So, now what we can do, we can actually look at this capital X g. So, which is those tuples x y, where x is coming from c I and y is coming from c j, such that this x y equal to g. So, if we write in terms of this x g, you can see that you can rewrite this as summation a I j g rho g, where g in g, where what is this a I j g? So, that is exactly going to be the cardinality of this x g, because for fixed g, so whenever you fix this g and we are asking the number of ways you can actually write this g as product of x y, where x comes from c I and y comes from c j. So, that is exactly captured by the cardinality of this set capital X g. So, where a I j g is nothing but the cardinality of x g. And what we are interested in proving, that it is indeed depends only upon the conjugacy class, it does not depend upon g, given g in g. So, once we prove that this a I j g is same as a I j tau g tau inverse, then that would imply that this t I t j is exactly equal to summation. Now, instead of running over g in g, we can run over all conjugacy classes I range from 1 to s, summation x in c I. So, maybe let me write a c k a I g x, and then we will have this rho of x. But if you have this for all tau in g and g in g, so then that would imply that t I t j is going to be exactly equal to summation, this I is k, k ranging from 1 to s. These are all constant values. So, this is going to come out a I j k summation rho x x in c k, which is nothing but t k. So, all we need to prove that this a I g does not depending upon the conjugacy class, does not depend upon g, it actually satisfies this property. Okay. So, let us actually try to look at it closely. So, recall what is the x g. So, x g is nothing but those pairs x y from c I cross c j, such that x y becomes g. So, now if we actually take some tau in g, we want to actually look at x tau g tau inverse, and we want to say that there is a bijective map from x g to x tau g tau inverse. And if we think about it, that bijection is indeed given easily. So, what we can do, we can actually take a pair x comma y, and then we can just simply map it to tau x tau inverse and then tau y tau inverse. So, if we actually take x y from x g, then we know that the product x y is g. Now, if we just take the conjugate on both sides, then we see that tau g tau inverse is going to be exactly tau x y tau inverse, which is exactly equal to tau x tau inverse again tau y tau inverse. So, that means if x y is in x g, so that would imply this pair tau x tau inverse comma tau y tau inverse is going to be inside this x tau g tau inverse. And it is easy to see what will be the inverse map. So, you take x dash y dash here, and then you simply send it to tau inverse x dash tau and then tau inverse y dash tau. So, that is going to be the inverse map. So, we have given actually very explicit inverse map. So, that actually proves this is indeed a bijective correspondence. So, that means the cardinality of x g is same as the cardinality of x tau g tau inverse, which is exactly a I j g, and then this is exactly a tau inverse I j tau g tau inverse. So, this indeed proves that a I j g does not depend upon the element g, it only depends upon the conjugacy class that it contains. So, that indeed proves what we wanted. So, with this we have that T I T j is nothing but summation a I j k T k, where k runs over 1 to s. So, that means this T I exactly behaves like algebraic integers. Now, how are we actually going to get what we wanted? So, recall that when we act T I on this representation V, so T I act as exactly H I divided by D chi of C I. So, this is our identity, this is how actually T I acts. So, let us go back. So, it is exactly acting as this H I divided by D chi of C I on V. So, that means if we substitute that in this equation, so we get, so this is going to give us that H I times H I divided by D chi of C I times H j divided by D chi of C j is going to be exactly equal to summation a I j k H k chi of C k divided by D. So, that means this number, this is our y. So, we can fix I. So, fix I, and this is exactly y, and this y j's varies. So, you can see that this y j is again linear combination of y k's. So, that actually proves that this H I divided by D chi C I. So, this is indeed an algebraic integer. Okay. So, this actually proves what I promised. Okay. So, we get that this H I divided by D chi of C I is an algebraic integer. So, using that, so we could actually get that cardinality of G divided by D is an algebraic integer. So, that actually proves that D divides the cardinality of G, and there is no reason that this chi of this number H I divided by D times chi of C I is an is an like integer or anything, because chi of Ci we do not know what it is. So, all we know that this is indeed some algebraic integer. It could be some complex number, not necessarily an integer or rational number. Okay, so I will stop here. This actually completes the dimension theorem. So, let me actually briefly like go through these results, and then like using this we will actually prove the very important application of representation theory of finite groups, so called Burnside's theorem. So, that we will do it in the next class. Thank you. We will stop here.